All right, let's start our classical field theory part 2. Of course, if you, this is the second week, so if you've been following along, you know that the notes for this are available as we move through this. Exclamation mark notes in chat for the notes if you're watching along on YouTubers. After, not live, after, then the beloved pony. If you're following along on the YouTube, then you can find the notes down in the description below. Let's start with a little bit of a last time. You don't know how. I should probably write something down, right? So let's talk a little bit about last time. Last time. You know what? I want a new piece of chalk. I'm going to treat myself. Treat myself to a new piece, a fresh piece of Hagaromo. Not sponsored, but should be. Anyways. And last time, what did we talk about? So we started, last time was the first one, and we talked about how particles are going to interact with each other, right? We ultimately know that a particle has to be able to communicate with, particles have to be able to communicate in order for them to be able to interact, change properties, and interact with other things. There has to be some sort of velocity of propagation of interaction. And what we learned from the principle of relativity, even from Galileo's principle of relativity, was that this principle of, or that this velocity of propagation has to be an ultimate speed limit, right? And that was the speed limit of information, and that was the speed of light. Now, what else did we learn? Well, we learned that, what else did we learn? Let's see here. Yeah, so we talked about how then the Galilean principle of relativity was then changed into the Einsteinian principle of relativity, which included time. I showed an example of a light clock, right? And how we could consider time in a different frame of reference. And then we looked at coordinate systems where we had our systems k and k prime. But ultimately, the big thing that we got to at the end of last time was we started labeling our intervals. S12 is the interval between any two events in spacetime. C squared t2 minus t1 squared minus x2 minus x1 squared minus y2 minus y1 squared minus z2 minus z1 squared, and this whole thing was brought to the 1/2. Now, this just defined an interval in space-time between two events. And this interval, we also talked about this interval in infinitesimals, as ultimately, this is the language which we want to do a lot of physics in, is when we talk about infinitesimally small change. Ultimately, you know, this leads to things like the principle of least action, which we've even already talked about today. So yeah, so we want to talk about things in infinitesimals, and this was how maybe a more commonly seen, definition of an interval. And then we showed by making some demands in 3 inertial frames that we ultimately have this invariance between any type of interval. Where an interval between two events in space-time, as long as both of these systems are inertial, not inertial in the same frame of reference, but inertial in different frames of reference, then this interval length is invariant, or that should be the same in any frames of reference. All right, so we ended here with this halfway through the interval section, so let's pick up where we left off. Let's define some notation. Notation is very important. Notation. So let's define some notation. Let's start off by saying t2 minus t1 is equal to t12, and subsequently x2 minus x1 squared plus x2 minus y1 squared. Nope, y2 minus y1, excuse me. y2 minus y1 squared plus z2 minus z1 squared is equal to L12 squared. Got it, Tyrion. I got it, Tyrion. Don't fear. And then we can write our interval as the following. S12 squared is equal to c squared t L12 squared minus L12 squared. And this is in the K system, right? So the inertial frame of reference as an observer is stationary, right? That was how we defined the K system last time. And then, of course, we could talk about what the person, or the observer in the K system, sees in a system of motion in the K prime system as S12 prime squared is equal to C squared T12 prime squared minus L12 prime squared. And this is in the K prime system. Okay? Now, what do we do with this? Well, let's consider, we have to talk about the invariance, of course. The invariance of this means that if these two different interval lengths are invariant, which they are, as we talked about last time, they need to be if we want to talk about, I think the example that Landau and Lifshitz was really cool about how the addition of vectors made it so that we had to consider an angle where we defined the change from one system of reference to another system of reference to be proportional to or a function of the velocity, so as a magnitude. So that was definitely problematic. Now, this is true, and we can also say, okay, well, let's consider if two events happen the same point in K prime system. Maybe the good way that might think is there's no change in length. So I could say, if I consider, me walking. Okay, so if I could see me walking, right? You see me walking, so I'm in K prime frame. I look at the ball. I stop looking at the ball. I look at the ball again. Okay? Maybe I could do it a little better. Okay, ready? I look at the ball. I stop looking at the ball. I look at the ball. Okay? That is two events that happened in the same place in X in my frame of reference. So, then I can say, that the L prime, that distance in the K prime frame of reference, is going to be 0, and I can get the following. C squared. Oh, let's talk about the interval of this then. The interval in space-time, S12, is equal to the interval in C squared, or interval, so it's equal to C squared T12 squared minus L12 squared, which is equal to C squared T12 prime squared. Okay? So now I set L prime 12 equal to 0, which was the indication that, yes, it is not moving in the K prime frame of reference. So what can we find from this? Well, this has to be greater than 0, right? Well, we'll just say it's greater than 0, okay? Let's just say it does move. So it's greater than 0. So what does this mean? Well, we can then write this down as saying S12 squared is greater than 0. This is what we call time-like. Okay? Time-like is causal, right? That's how we say two events that happen that are time-like separated are causal. What does that mean? That's everything. That's everything that you observe. Everything that you observe that does not propagate at the speed of light is two events that happen causally. So anytime that let's see, what did you do? Let's literally think of anything. You looked at your computer screen and then you opened a tab. Those are two events. Those have to happen causally. They have to happen where the distance, the proper length, the length of the interval between those events has to be greater than 0. That's time-like. And we'll show more about that with the light cone. But then we can find a time between two events as observed in the K system of two events happening in K prime. So for instance, someone who is at rest observing me looking at the ball twice, and what would they see? Would they see the same thing? Would the times be different? And it turns out that the times would be different, right? This is also equal to the interval S12 over C, and this is going to come back. Well, actually, I don't, in this form it's going to come back. But let's go back and say, okay, well, let's consider this form again right here. Okay? Okay, what happens if we let the time acting between the two events be 0, okay, but then the length between the two events be non-zero, be greater than 0? Okay, what does this mean? This means that we want simultaneity, okay? Two events happening, different spots in space, same exact time. And what does that mean? And of course, we can think about simultaneity in one frame of reference, but now we're into the beast where we have to evaluate it in 2 frames of reference. And this is ultimately where we found out that simultaneity does not work. And let's think about that. So what does this become? Well, then S12 squared is equal to minus L12 prime squared, which is less than 0 because it's minus, right? We set this equal to 0, and we have S12 is equal to C squared T12 squared minus L12 squared, which is then equal to minus L12 prime squared. That means it has to be less than 0. So now we have another problem, and that is that we call this space-like separated. Separated. Keep them separated. These are said to be imaginary intervals. The problem really is that we have this squared here. You know, it's not negative space. It is a negative space squared. So when we want to find the actual interval, we end up having to take the square root of a negative number. Problems. Yes, many problems. Now, if you are just tuning in, make sure that if you would like to follow along in the notes, you can type !notes in chat. Or again, if you're watching on YouTube, the notes are in the description. Let's look at the figure there, the light cone, which I'm going to draw one on the board. So even if you don't want to follow along in the notes, then that's fine. I'll draw one on the board. Roo-doo-doo-doo-doo. So the light cone. Now, the light cone, we had these coordinates last time where we had t set up here and x set up here. CT really is the right way we want to talk about that. And yeah, an x over there. And then we want to say, okay, well, let's have some defining moment where this space, time-like and space-like, you know, meet, okay? And that, of course, when the speed of light, or when the whiff. That is, of course, when the events, the distance between the events, the interval, is c, okay? So we can have this slope where any events we draw along that slope are, as you would imagine, rise over run. So ct over x, let's write down the relationship. What happens if c squared t squared minus x squared is greater than 0? Well, that's time-like. What happens if c squared t squared minus x squared is less than 0? That's space-like. And then what happens when c squared t squared minus x squared is equal to 0? And we say that that is light-like. Can we solve this and take a look at it? Of course we can. Let's bring x over to the other side. C is equal to x squared over t squared. C squared is equal to that. Take the square root of all of that, and you get c is equal to x over t. The change in space over the change in time is equal to c. For c equals 1, young man, it is for c equals 1. How did you guess? Yes, it is for c equals 1. And that's oftentimes why we set c equal to 1, is because we get a really nice graph. And it looks really good, and who cares about c anyways? But there's other consequences for that too. We're not going to talk about any of that. Does that I show up when we have a space-like interval? It does. It does, and that's in... Now, last week, Tropical said that they found the PDF, and I have also found the PDF of LNL online, so you're more than welcome to look at that for... I think I found it for free. I don't know if it's free or not. But it does show up. It shows up in the sense that... let me see if I can do it really quickly. L12 prime squared is equal to L1... No. Yeah, L12 squared minus c squared t12 squared is equal to minus s12 squared. So if I wanted to know what L12 is, I end up getting the square root of L12 squared minus c squared t12 squared, which is equal to the square root of minus S1. No, minus. Yeah. I S12. There we go. Tyrion, you're so corny. All right. So that's why it's imaginary interval, right? And space-like. So let's talk about let's keep talking about this then. So we can define this light cone such that if we have, and now I'm going to make it two-dimensional and spatial. That's why we draw something like that, because now we can make it two-dimensional by just establishing a third, coordinate system. Like that type of deal. But anyways, that's why we call it a light cone, because we normally think about it in two spatial dimensions and one of time, but you can easily extend it to three. Like I said last time, you can easily extend it to three spatial dimensions. For all intents and purposes, like in this one, we're setting y and z both equal to 0, so it won't matter anyways. But all right, so then in this light cone, we can establish two events happening. Let's have one event happen here, and then one event happen let's make it here. There we go. So that it's still causal, right? We could call this event A and this event B, and that they're connected by a interval ds. Let's just say SAB. There we go. That looks better. And that interval is going to be clearly time-like, right? Because it happens inside. Now what happens if we have event C happen out here and the change in the length is far greater than the change in the time, right? E doesn't even need to be that exaggerated. Like it can be a lot less exaggerated than that. And what happens if we do that? Well, we get, something where the interval of SAC is clearly going to be much less than 0. Let me see. So that's how we use light cones to define this stuff. I have more videos on light cones that go into more detail about these things. I feel comfortable saying that this is where I want to move on from. If you have more questions, of course, you can ask them. But I do have more videos out that we did previously on special relativity that go into more detail about timeline or about light cones, and I will put them in the description below for the YouTube VOD as well. Now, let's move on to proper time, okay? Proper time. So you might say to yourself, I would like to measure how time will tick on the watch of someone in a different frame of reference. We talked about it, we briefly mentioned it, but we didn't actually try to calculate it. And that's something that we could do by just revisiting one of our older equations, and instead the one originally where we had S12 squared is equal to C squared T12 squared minus L12 squared is equal to C2 T12 prime squared, which was greater than 0. That was how we derived that it was time-like. And then let's say, okay, I want to do that, except let's talk about the infinitesimal form of it. So ds squared minus C squared, equal to C squared dt squared minus dx squared minus dy squared minus dz squared, and then this is going to be equal to C squared dt prime squared. Again, this was the one where we set the distance between two events in the moving frame of reference to 0. Tactical assault pigeon. Thank you for the follow. Welcome in. So this was when we set the length differences to 0, and now we want to solve for dt prime. Dt prime is going to give us the means to find out how a clock will click, how a clock will tick. I have to be careful about the words that come out of my mouth. In a moving frame of reference. There we go.
A taco click.
Oh, man. A taco click. Good. Nice and safe. Okay. Then we can notice that this term here looks like what? Well, that dx squared plus dy squared plus dc squared is just going to be some three-dimensional version of change in three coordinates, and over dt squared is going to be the change in time. So assuming that it's constant, we need it to be constant for these rules to work, we can replace that with the velocity of the object in the moving frame of reference. Don't think about the rooster. Oh, no. So then we can integrate both sides. Let's dt prime, let's integrate both sides. And t1, t2, these are both primed. Woo! Of course, these are happening in the primed frame of reference. These are happening in the normal frame of reference. And we can find out that where Landau and Lifshitz stops is t2 minus t1 is equal to the integral of t1, t2. dt. This is a little bit sketchy of an integral because we kind of got rid of dt. We kind of absorbed it into v and said it has to be constant. That's true. It does have to be constant. V has to be constant, that is. But as long as we set va equal to a constant, it's not that big of a deal. We can sort of figure out how this is going to behave, right? And the first thing we would want to do is say, what is going to be the time length difference for two things that are not in a moving frame of reference? So i.e. two things. I don't understand anything. We'll just hang out. We're almost done. After this, we're going to be playing our physics challenge, which doesn't necessarily require a lot of physics. It's more, this week is quotes, physics quotes from famous people. So it should be a lot of fun. But anyway, so now let's do our first exercise and just say, what happens if V or the system of reference between the two systems, so this is in the K prime system, this is in the K system, what happens if they're in the same inertial reference frame? Well, if they're in the same inertial reference frame, V is equal to 0, which means we get the square root of 1, which means we get that the difference between times in this one, or the rate at which a clock will tick, is the same rate at which a clock will tick in K. Good. Once we start changing this, once V becomes non-zero and starts becoming something, let's just say like 1/2 of C, then we can derive, or take the integral, or slow down, simplify this. We get 1/2. What's squared? 1/4. Take the square root, then we subtract it. 1 minus 1/4 is 3/4. Take the square root of that, multiply it by D, and we get the way that the clock is changing. The clock that's ticking off in the K prime frame of reference will tick off at a slower rate than the clock that's ticking off at the DK, or in the K frame of reference. And we showed that last week when we talked about that light clock example, right? All right. That's proper time. There is a weird thing that we should talk about briefly. Hey, Pivot Ups, what's going on? It's plus oneing. I just didn't want to be the first one to say it. Does the present exist? That's a good question. And yes, of course. Because ultimately we get into the dangerous question of reality. What is real, man? Am I real, man? Are you real, man? And ultimately, we have to define that as something. And I would say the most simplest explanation of reality can I physically calculate something, measure that, and test that calculation or test that prediction? And if the answer is yes, then I would say whatever it was that I was testing is real. So can I do something with this stuff? Can I make up a formula where I say, at this time I will do this, at this time I will do this, and then that happens, then I would say, yes, those present times are real because at that time I am measuring something and I am getting an answer, and all of that fits very nicely into this picture, which would be, yes, the present is real. I don't know if that was a joke question or not, but I went there. Ash, what's good? You are really old man. Thank you. Good to see. I can read some of the things on the board.
Got their numbers.
We got there some numbers. What you got there, boy? No numbers. Okay. We have, let's talk really quickly about the one confusing thing that I'm sure everybody's thought about. Well, if I'm in my K frame of reference and they're in a K prime frame of reference and moving, and I'm looking at their clock and I'm measuring it, it's gonna tick slower. Yes, we talked about this. If they're in K prime frame of reference and they're looking at my clock tick and they're measuring it, is it going to run slower? Yes, it's going to run slower. That's what these things tell us, right? Just because you change from one frame of reference to the other frame of reference doesn't mean it's going to change the laws of physics. It's still going to run slower. Mr. Physics Man, you have a contradiction. And I say nay. I do not.
3 equals 22 sevenths.
Okay. Okay, thank you. I have. What you on about 3/4 in this integral? I just said what happens if. I don't know what I was saying with 3/4. I was not. I was clearly high on something. No, that was a mistake. I said what happens if your velocity is half the speed of light, and then I did it all wrong. Did I do it all wrong? I don't know if I did it wrong or not. I'm not going to bother with it. If it's half in v squared, you square it. It's a quarter. C's will cancel, and you have 1 minus a quarter. You get 3/4, and then you take the square root of it. I don't know. Anyways. So if you look at your time clock, the time clock goes normal, but if you look at someone else's time clock, they go slower, is what I heard. Yes, if you look at someone else's time clock as they are traveling at a high enough velocity, it will tick off at a slower rate. As they look at your clock, it will tick off at a slower rate. Sounds like a contradiction, but it's not. Yes. And I'm not going to go into too many details on why it's not, other than we have to accept a few things to be true. Namely, they have to move in a specific way, which is a linear path with constant velocity. Okay? Once you start changing that path, i.e., if it's a rotational path, or if it's or if they stop and turn around and come back, then you start adding non-inertial frames of reference, and things change. Now, I'm not saying whether or not these things don't hold or do hold or don't hold. That's not for this class. We're not going to, class. Woo, I've been teaching a lot lately. It's not for this, discussion series. But once you do that stuff, inertial frames of reference change things. It does not say anything about the twins paradox either, okay? The twins paradox is well understood. It is. I promise you, it's well understood. It is just to say that once you change things, and you stop considering consistent linear velocities, it is no longer an inertial frame of reference. Okay? So that's it. We're not going to go into that. Yes, the twins paradox is definitely.
Explain it with entropy.
The twins paradox is definitely confusing, and it's definitely one of these things where science communicators like to be like, yeah, you just zoom off close to speed of light and come back, and you're going to be super young, everyone's going to be dead. That's crazy, and physics tells you that's true. And they're not wrong. They're not wrong. But once you speed up, slow down, speed up again, and come back and slow down again, you're now doing inertial things. So the stuff that we talked about here is not going to apply to that. At least not as cleanly as it's applying, as I'm applying it right now. Okay? And that's just all we're going to say about that. Okay? But no, the twins paradox is true. You didn't do it.
Than the speed of light.
What's this? Yeah, I know. Just go fast as the speed of light. It's easy. It's easy. I don't understand what the big hubbub is. Just go fast as the speed of light. If you want to talk about how it looks the same in different frames of reference, then you could say, okay, well, what happens if, and I'm going to convolute this one more time for the sake of convoluting it, is that what happens if I see somebody and they're, light years away? Let's just say 1 light year away. So I'm here. This is for you, Bree. You wanted stick figures. I'm here on Earth. I'm tall, right? So it's kind of accurate. And Tyrion's over here as an alien, which is also accurate, right? And we're both wearing top hats. And then NC is in the ship right here. And he's, speeding along, right? And he passes me, and our clocks read the same time. 12:30 or whatever, 6 o'clock. whatever you want to pretend that to be. And our watches measure the same thing, right? Now, NC is traveling along at half the speed of light towards Tyrion, who is 1 light year away. Okay, now you can run these calculations yourself. I'm not going to bother to run the calculations. I'm just going to tell you the following thing is true. Okay, once NC gets to Tyrion and measures his clock with Tyrion, we no longer know anything about my clock. In order to figure out how fast I'm reading NC's clock from here, then I have to wait for the information from NC's clock to arrive. So not only do I have to wait for NC to get to Tyrion's location, but along the way, the information starts taking longer to reach me. By the time the NC is here, any information that I could get from NC's clock has to take a light year or more to get to me. So this is like one of those things where it's like, yeah, I'm going to purposefully, what's the word? Obfuscate? Complicate something. Because it's very complicated. It's not nearly as simple as just saying, okay, if he goes out here and he looks at my clock, then I'm going to say, we're going to have this, different times, but he's going to look at Tyrion's clock and it's going to be at the same time as mine, so what's going on? That's a contradiction. No, it's not. It's just really complicated and you've reduced it into something that you think is not complicated. But yeah, it is very confusing. So this is like the 8-minute delay for when sun stops shining. Yes, exactly. Obfuscate. That's it? I thought it was obfuscate. So yeah, so don't try to take a simple topic, and that's basically all Landau and Lipschitz said. It's just like, this has an apparent contradiction, but it's not. It's easy, and then they explained why, and then it was like really complicated, their explanation. So we're not going to go too deeply into that. But what I said is good enough for now. So let's talk about Lorentz transformations really quickly, and then we're done. So we're on section 4 of the book now, the Lorentz transformations. Lorentz with a T, transformations with an F. And now we want to talk, so we're just going to quickly talk because they were mentioned last week, about Galilean transformations. These would be what you would do before Einstein. If you wanted to know how something is going to look in a moving frame of reference, you would do the following transformations. Then we're going to see these, and then next week when we start, we're going to show how these don't work. So if I wanted to look at the x-coordinate of something moving, I would see that the x-coordinates follow the arrangement as follows. T equals T prime as follows, right? In the moving frame of reference, x is going to be changing by, some vt, and nothing else changes. Now, ultimately, if you know special relativity, you know that this is wrong because of this. Not true. It's also wrong because of this, which is not true, because having a velocity that's not absolute means that, again, we come into that problem where I say, okay, well, instantaneous information transfer can't happen. And it can happen. That was the issue, was that it could happen. But ultimately, we know that information transfer, what we talked about at the beginning of last week, was that information can only transfer at some absolute speed, or else the laws of physics themselves have to change. And we can't be doing that. No, we can't be doing that changing laws of physics thing. So we have to make v equal to c as a maximum speed limit. I guess it doesn't equal c unless it's moving at the speed of light. And then some other things happen, which we'll talk more about next week when we go into Lorentz transformation. So I did want to just briefly mention this as we talked about it last week. And it's the beginning of the chapter, or the section on Lorentz transformations. So next week we're going to start by saying, okay, let's take a rotation of coordinates into account and see what happens to the time coordinate under certain rotations. And we're going to find out all sorts of cool, fun things happen. And that's our classical field theory for the week. How are we doing on time? How do we do? 2:39. Okay, that might be over 30 minutes again. That's about the speed of where we're going to be at, I think, for how fast we can go at these. And Tyrion's over here as an alien, which is also accurate, right?